Honestly, Pages is working for me.
Okay, cool. Let me know.
So this is the camera control.
Oh, is it?
Yeah.
Okay, so.
Pointed which is back over there.
Oh, it's working. Okay.
And so yeah, obviously left, right, TW or like zoom in, wide angle. With help is stuff like that.
Okay.
Yeah, just don't have some of the numbers. This is just saying
Okay. Sorry for the delay. So while I'm signing in, quick reminder: the first midterm is fast approaching. It's not the usual reaction here. It's just over a week away, right? So October 10th. Yep, Thursday. 7:30 to 9 p.m. If I remember correctly, the location is XT 150.
Is that the big?
That's the big one, yeah. Because I want to have both sections at once, and so this. Yeah. So that's midterm 1. If you have accommodations, hopefully you have emailed me and heard from me. If you have conflicts, you should have emailed me by now. And also, again, hopefully heard from me. And but you should have, if you have conflicts, you should email me what other times that week are available so that I can arrange for conflict exam time that works for most people. Because the exam is next week, there is. Because the exam is next week there is no homework and no quiz. Okay, obviously there is still this week's homework and quiz, so don't forget those. But yes, next week there's no homework, no quiz, and no help session for the homework. There will be an exam help session. Also, the practice exam will be released tomorrow.
This is the first class that has a practice exam.
The solution to the practice exam will only be released on Monday, so I'm still gonna, try without succumbing to the temptation of looking at the answers. And my suggestion would be try and take it under exam conditions, right? Try and take it under time conditions, because usually, one of the tougher parts of the exam is trying to do it within a set time. Okay. But we will. Oh, and of course, since people will ask, the first midterm is covering these sections, so that is not including friction, right? So today's class will not be on the exam because you haven't had a chance to do all the problems on friction and such. But everything up to then will be there. But yeah, we are going to continue learning the material. So we'll be learning about friction today. Yeah. Questions? The other thing I recommend is on Moodle, you will find a document in next week's thing, core skills for the midterm. And so it's basically just the learning goals that we've been doing each week. But I do suggest you look at them, and it'll basically say stuff like, oh, students should be able to like go from velocity versus time graph to an acceleration versus time graph and stuff like that. So you can go down the list of skills and like, oh, am I comfortable with this skill? Am I comfortable with that skill? And then if you're not, then you can find a corresponding problem and practice those skills. All right. Okay. So last time, we were. Yes. All right, so this is what we ended on last time. We didn't really have a chance to discuss it. So yeah, we'll go ahead and start with discussion actually. You're obviously correct that there's more than one correct answer. So what I want you to discuss instead is about which statement is false. Okay, which of these four statements is false? Go ahead and use that.
It must be considering
Yeah.
It's one side. There's actually students right now.
Well, it's like accelerated. They're probably well, it's like the roadway accelerates. It's not but
Yeah, I don't really know what we're doing. Since the kids are like completely still,
yeah,
but
it's like
they're just further.
or it's like moving, but it's like I don't know.
That's true.
Yeah, but I also. Is there further like
But if it's like
I guess like it could be moving at a certain.
but what about like on the ground?
And then.
Yeah. Yeah.
If there's no one on the ground, then neither of them move.
Yeah.
What else is just a movement?
Yeah.
Well, like in theory,
Because I feel like A and B kind of goes there.
yeah, and they'll still be waiting.
One of the
Like, I think that's
All right. All right, we're voting on which statement is false. Okay, not which statement is true, which statement is false. All right, go ahead and show me your votes. Okay. All right, so mostly for A, that is correct. A is the false statement. So we will look at that in more detail. So we have the teams. Yeah, okay. I don't know. Prompter doesn't seem right on that, but okay. So Slytherin, Gryffindor. All right. So if we look at the forces on Slytherin, what are the forces on Slytherin? force of tension, so there's the rope on Slytherin. R for rope, so okay. R on S. And yeah, FG. There's force of gravity, there's force normal. And what else? Someone else said something? Yes?
There's a friction force.
There's a friction force, exactly. And who is exerting that friction force?
Slytherin on ground.
Well, we're looking at forces on Slytherin. So ground on Slytherin, yes, exactly. Ground. Ground on Slytherin. And it's because this force is larger that overall their acceleration is to their side and their way. So, but wouldn't that would seem to imply that, oh, won't the pull that Slytherin is exerting on the rope be greater than the pull that Gryffindor is exerting on the rope? But the crucial point here is that the rope is massless. Why is that important? Well, because we have F net equals MA. So this tells me if I have a massless rope, even if it's accelerating, right, this side is going to be 0. Which means the net force on the rope has to be 0. Right now, there are only 2 forces on the rope. There's the force of Slytherin on the rope and the force of Gryffindor on the rope. So those 2 have been E. Right. So yeah, so massless rope, we see that if there are only 2 forces, then those forces are equal. And so yeah, there's the magnitude of the force of Slytherin on the rope is equal to the force of Gryffindor. Questions? Yes.
Does the thing with the massless rope like have like greater implications? Like I feel like if we had like that seems like a big thing if it just like having a massless object means automatically that net force is 0, like.
Yeah, no, I mean it's sort of it's unusual and convenient, yes. Yeah. Yes.
So the problem doesn't like just the problem doesn't say if it's accelerating or not, but since it's massless, then it's not accelerating.
No, it doesn't say it's not accelerating. It is regardless of whether it's accelerating or not, that side is going to be 0. Yeah. Other questions? Yes.
What if the rope had mass?
Good point. If the rope had mass, then we'd have to look at are they moving at a constant velocity or are they accelerating, right? And if they were accelerating, then yes, one of the forces would have to be greater than the other to give a net force in that direction.
And would it still be true that the friction forces on the ground would still be the same kind of?
Well, definitely for Slytherin, it would be true that the friction on the force or friction on Slytherin from the ground would be greater than the rope on Slytherin, because otherwise they wouldn't be accelerating. That, yeah.
What about the friction of Gryffindor on the ground?
Would have to be less than the force of the rope on Gryffindor, because the rope is what is then making them.
Yeah, so what would be creating the tension force if the rope is massless?
Their pull. Yeah, so the way to think about a string is that it is like a very tight spring almost. And with a spring, you know that if you stretch it, it will try to contract, right? And so the same idea here with the string, except it doesn't stretch at all, but it is always trying to like pull back together. So the tension that it exerts on other things would be like this. This would be force of rope on Gryffindor, force of rope on Slytherin would be like that. If we look at the rope's free body diagram, we would have force of Slytherin on rope and force of same because it's massless, force of Gryffindor on rope. Yes,
Isn't there also gravity? Like, why is the rope not falling down? Are those two like kind of off to the sides?
so if there was mass, then we'd have to worry about gravity, right, because it's massless, yeah.
Is this like, does this have anything to do with like this third law? Like, I don't know, I'm just kind of confused, cause like, wouldn't there be like Slytherin is like exerting like a force on the rope, so like the other side of the rope is like exerting like, I don't know, like action, reaction pairs and stuff, I'm just confused.
I mean, if it's massless, it's sort of, I mean, action reaction is going to hold regardless, right? If it is massless, then you get a lot more equalities because these will have to be equal. Whereas before, if it had mass, they wouldn't need to be equal, right? But it is still true that like, oh, force of Slytherin on rope and force of rope on Slytherin, those are action reaction pairs, so they have to be equal regardless. All right, other questions? Okay, so yeah, just to quickly run through the other options. Well, if A is false, well, I mean, A and C can't be true at the same time. And we've explained why A is false, and we've explained how, because it's a massless rope, C is and B is also true, we've seen, because otherwise Slytherin wouldn't be moving. Well, D is usually. All right, skip ahead a little bit. Oh, actually, yes, okay, we'll do this problem quickly. This isn't the friction problem, but it is about pulleys and it is useful. Let me clarify. Oh, there's a conference there. Let me clarify that there are two pulleys here, right? There's this pulley which is attached to the table, and this pulley which is not attached to the table, right? It is hanging by this rope, right? This rope goes from one over this pulley down, and it's holding up this pulley, right? And then the center of the pulley is attached to blocked. I won't give you too long. Ready to vote. Okay, all right. Let's see. Mostly. Well, okay. Briefly, go ahead and discuss.
If you pull down, if you pull on a rope, like clear as a pull, how far would it be? Yeah. But now the rope has both sides of the rope have to move down. So then how many
on both sides.
No, like, I think that.
It's two sides.
I think it's I don't think you guys
So if you pull the rope to depend on how far it moves, like without but now you see that if you're bringing it down and suddenly both sides of the rope
One would move 2 times. Two now to travel up on that side.
Okay, but what about, so it once you moved down, both of the ropes. Okay, but I was block 2 is still moving down. Total.
How much? All right. Right, okay, pretty much universal for D. Yeah, let's see. Zalim, you want to give a shot? Sure.
So between the height of the top pulley and the bottom pulley, there's like double thing. So just like going off of intuition there, it seems like if the right block, the block number 2 moves down by 10, then the rope has to travel like twice as much, it has to be spooled down. So then block 1 would move right 20 centimeters.
Exactly right, yes. It might become clearer in this diagram. Basically, if block 2 moves down 10 centimeters, it needs to add 10 centimeters on both sides, right? And this rope has to come from somewhere, so this would have moved quite to scale. But it would have, block 1 would have moved 20 centimeters, yes. Question? Someone mentioned the gym and about how with pulleys it becomes easier to when we get to the concept of work, we will see that yes, there's a trade-off. That pulleys basically, depending on the arrangement of pulleys, you can exert less force, but the trade-off is that you need to move a greater distance to do the same amount of work, basically. So yes, we will see that when we get to it. All right, let's get that. Oh yeah, discuss this very briefly. Just read the question, and I'll sort of sketch it on the board here.
Dr. Paily,
Yes.
just so you know, the camera can't see.
Oh, you
that
can't see. Oh, okay, good to know. Oh, I can use that whiteboard over there. All right. So we have this arrangement. And in this case, again, this pulley is fixed, this one is not, it's resting on this rope. There's only a single rope winding its way through like that. And then there's this separate cable attached to the platform. And then there's the worker there. Okay, so what is the advantage of do I have the colors? Yes, okay, should have the colors. What's the advantage of that pulley arrangement? So because this is a single rope and it is massless, we've seen that, oh, the tension will basically stay the same throughout. So then let me, let me what do I want to do? Yes, let me cut off the system like this. Okay, so you can see that I've enclosed the man, the platform, one of the pulleys. All right, and I've cut across the rope 3 times. And the pulleys and the platform we said are massless to make life simple. So we just have to worry about the mass of the man. And so if I draw the free body diagram for the system, I will have mg pointing downward, right? And then what will I have pointing upward?
Two tensions, I guess one tension.
Three tensions, yeah. Each of these has tension T, right? It's the same magnitude because it's all part of the same massless row. So you can either write it as like 3 force of tension, or you could, I don't know, you could draw like this, I guess, if you wanted to make it clear. But yeah, you have 3 forces of tension balancing the force of gravity. And so you get, since the acceleration is 0, then you get that 3 times the force of tension is equal to mg, or the force of tension is mg over 3. And so this shows you some of the advantage of the pulley system. You can, right, hold yourself stationary, even though with much less than your own weight, just 1/3 in this case. Yes.
The trade-off being that in the distance that you would have to cover, like there's some sort of equivalence.
So if you want to raise the platform like 5 centimeters, then you'd have to pull it 15 centimeters because each of these would need to change by 5 centimeters. All right. This is why old sailing ships had so many like pulleys and whatnot in the rigging, because they had these huge heavy sails that they needed to turn, and the pulleys helped to make that easier to do. Okay. All right. Now let's finally get into friction. Oh, that took long. Okay, we'll come back to this in a moment. Actually, how about this? Let me ask this. Ready. And all right. Pretty much everyone for B, yep, force of the ground on your feet. So you can sort of imagine that, yeah, when I'm walking forward, I'm like pushing back and downward, right? And so you can, yeah, okay, you can imagine leg, shoe, yeah, there we go. And so you are pushing down and backward like this. And so we can split that into 2 parts. So this is your force, you on ground. And you can split that into 2 parts. You can split that into parallel to the surface part and a perpendicular to the surface part. And by definition, this perpendicular to the surface part, this is what we call normal force. Right, so this is F normal U on ground. And this is what we call the friction force. So yeah, this is the force of friction with U on the ground. So just like the normal force, friction is something that happens when you have 2 surfaces in contact, right? And when they interact with each other, you can break up the forces between the surfaces into a part which is perpendicular to the point of the surface at the point of contact. That's the normal force, and a part which is parallel to the surface, and that is the friction force. Okay, so then, yeah, these are the forces on the ground. So we can anticipate that the forces on you would be in the reverse direction. So yeah, there is a normal force of the ground on you. And there is a forward frictional force of the ground on you. So there's a common misconception that friction always stops motion or like acts against motion. But you can see in this case, friction can actually cause motion, right? What the friction is doing here is it's trying to prevent slippage, right? If there was no friction, your foot would slip backward. And so to stop that, the force exerts a force on you forward. And correspondingly, there's a Newton's third law, there's friction by you on the ground. Questions? Very common to get confused about friction directions, so like, do ask questions. All right, cool. All right, let me, yes, I'll put the screen up for a little bit. Use the main board. All right, so what is happening in friction and what are the different kinds of friction? Typically people talk about three types of friction. There is static friction, kinetic friction, and rolling friction. The order is like static friction is greater than kinetic friction is greater than rolling friction. Since rolling friction is the least, this is why we use ball bearings and stuff because you're changing it from sliding friction to rolling friction, which is much less, so you get much less wear and tear. We will not really talk about rolling friction in this course. We'll mention it briefly when we get to rotational motion and rolling, and like tell you where it comes from, but for the most part, we're going to ignore rolling friction. Kinetic friction happens when two surfaces slide past each other. Right. Static friction, obviously, they're not sliding past each other. So, let's see, it's a good example I can give. Oh yeah, I can use the. It's a lead brick. Come later at the end of class, you can come. It's great. It's quite heavy. All right. So I have lead brick on a folder on the table, and so if I start pulling on the folder, right now you can see the brick is not moving. Okay. But as I increase the pull, eventually it will start to slide. Okay. And so what we're seeing there is this transition from static friction to kinetic friction. So static friction, basically it will try to keep the surfaces like stationary with respect to each other, right? And as you increase the pull, the static friction will perfectly counteract that and exactly cancel it out so that there is no acceleration. But it can't do that forever, because if it could, then nothing would ever start moving, right? So there is a maximum static friction force that you can reach, which differs from case to case. But there's a maximum static friction force you can reach, and then if you pull even more than that, then it transitions from static friction to kinetic friction, and you get sliding going on. So yes, the important things to remember are static friction is an adjustable force. And so you should determine it from your free body diagram. As we said, there is a limit to how big it can get, and so the force of static friction max, we will say, is μs times Fn. Now Fn here is the normal force between those two surfaces. μs is called the coefficient of static friction. Few important things to notice about this equation. One is, well, if this is a force and this is a force, then what can we say about μs? It's a constant, but more specifically, well, let's go with
Scalar?
Scalar, true, but then yes, I mean
It's dimensionless.
it's dimensionless, yes. So yeah, it has no units, right? Because this is already newtons, this is also newtons. So yeah, this has no units. So it is a number. So yeah, it's a number. The other thing is, notice that I did not draw vector arrows on top. Right? This is intentional. These do not point in the same direction. Right? Remember how we defined them. Normal force is always perpendicular to the surfaces. Frictional force is always parallel to the surfaces. They do not point in the same direction, but they are proportional to each other. Incidentally, this is a simplification. Friction is a very confusing and complicated area of study in physics, and the study of like friction is called tribology. And so people will also talk about like nanotribology, where it's like, oh, you have like maybe something on the nanoscale like moving past a surface. This is like a simple model that works for most cases, but it's by no means always true. Like a more general formula would be something like, okay, friction is C1 Fn raised to C2 plus C3A, something like this, okay? Where Fn is the normal force, but like C1 and C2 are some constants, and A is the area. And so what we see is that in the simplest model, there's no area dependence. But when you look at more general cases, there is actually an area dependence. Questions? Okay. All right, let's do a quick demo. About 10 minutes, all right. All right, so got a block, some sandpaper on one side of the block. We have this, what do we call it? Force meter. So basically all this is, you can't see, but there's basically a spring inside here. And what it does is the more force I exert, the spring, changes, and you'll be able to see how much force I'm exerting. So right now it's only about 4 newtons, and okay, a bit more of that, and you can see that it's sliding. Let me make it clearer by adding some weights. That will hopefully make it a little bit easier to observe. So because I've added some weights, I've increased the normal force between the block and the plank beneath it. So that should increase the frictional force. And so, yeah, you can see that I'm going well beyond 8 newtons now, 12, 16, 20, right? And then, and also it might have been a little tough to notice, when it transitioned from stationary to sliding, the needle went down slightly, right? And so that's part of the kinetic friction is always going to be a little bit less than static friction. Otherwise it wouldn't start moving, right? All right, and so what is happening? Why does friction happen? And why do we, like in the simplest case, why do we say there's no area dependence, and why does it become area dependent in more complicated cases? Erasers there, chalk is here. Yeah, okay. So basically, even a surface that you normally think is smooth is on the atomic scale usually rough. It's, I mean, these days with advanced machining, you can get like even atomically flat surfaces, but those are still rare and expensive to get. So usually, surface, even if it looks flat, is rough. That applies to both surfaces. And so what that means is that even if you say that, oh, there's like this much area in contact, usually the actual contact is only happening at a few points, right? And what is happening at those points is that the molecules and the surfaces are being pressed together and they're forming a temporary bond. Okay. And so when you start to try to slide one past the other, well, then you're stretching that bond, right? And it doesn't want to break, and so that is the friction. It's trying to stop the sliding. Okay. But eventually you supply enough force and it'll break. And then in kinetic friction, what's happening is that, yes, again, all these points are sliding past each other and they're forming and breaking bonds, but they don't have enough time to like form a strong bond, so you get a smaller level of friction. Yes?
If you had two perfectly smooth things, would
Yes.
would there be high friction because all the bonds are connecting, or very low friction where they just slide straight past?
No, you typically get very high friction. There's, what are they called? I forget, there's this like set of blocks where they're like machined really smoothly, and then if you put them together, they like stick together so well, like you not put glue or anything, they just stick together so well that it's really hard to take them apart. I'll try and look up what they're called. But yeah, if you get like atomically smooth, yeah. Yes.
So it's not like, at least during kinetic friction, a bunch of small contact forces. So I get a lot of small normal forces acting against each other. It's the bonds.
Yes, I mean, we would, because the normal force we define as like perpendicular.
But if the surfaces are, say, bent, then.
Oh, I see, gotcha, okay. I'd say we tend to model it as like little bonds, yes. But I mean, you are correct, it is complicated because, you know, depending on the strength of the material, this shape might deform as you try to pull it, right? And so, yeah, it does become a bit complicated. Yeah, and so then, oh, yeah.
I mean, you could akin that to the sandpaper sanding down the wood, like it gets more smooth.
Well, to an extent, yeah. Yes, there is that sort of deformation and effects on each other, yeah. Okay. So the area, oh yeah, so why it doesn't depend on area is because what we would argue is when I put the block on the plank this way, it's got lots of points of contact, right? And they're all deformed a little bit and forming bonds at those points of contact. When I put the block this way, there are fewer points of contact, but each of them has a bigger column of mass on top of them. And so they get deformed more and they form like stronger bonds. And so in what you could say is the low pressure limit, there's no difference between these two. It's either like lots of points of contact with like just a little bit of deformation each, or like a few points of contact with a lot of deformation. But once you go into really high pressure, then like you basically like they're all deforming a lot. And so then it does become a matter of like if they've deformed to the maximum, then it's like the more number of points of contact, the more friction there is. And then there is an area dependence because then you have more points of contact. But for the most part, we'll work with this simplified model where it doesn't depend on it. All right. Yes, okay. Yeah, we will add on this question. I'm drawing a free body diagram. Anyone need more time? Yes, a little bit more time, okay. Okay, get ready. And show me what you think. All right, for a variety of answers. Yeah, no, okay, I'll just tell you. The answer is A. So why, now you might ask, wait, why isn't it D? Why isn't it US mg cosine theta? Isn't the normal force mg cosine theta? The normal force is mg cosine theta. But remember, it's not static friction equals mu s times Fn. It's maximum value of static friction equals mu s times Fn. And nothing here said that we were at the maximum value. All we said was that it is not slipping. And so what you should do is draw your free body diagram, determine what force is trying to make it slip. In this case, the force that is trying to make it slip is mg sine theta. And then static friction will exactly counter that. And so the magnitude of the static friction force is the same. All right, I'll draw a free body diagram and we'll talk about this next time, but yeah. So
It's a lot of their actual. Should be fine.
Yeah.
I will.
Yes. Oh, so the force of the person is downward, but the force of the rope, well,
Rope on the person.
exactly.
Thank you, Zach.
Thank you.